Howdy everyone, we are Group 24. My name is Jin Cao. Here's my teammates Yuan Long and Arumi. Today we want to introduce the paper, The Federated Learning with Fair Worker Selection. Federated learning is a subfield of machine learning. To talk about that, I want to compare it with conventional machine learning. Traditional machine learning is running on a single server, and users need to upload all the data to the server. The data is stored centrally, so there is a risk for data leakage, and it may raise privacy concerns. So here's come to the federated learning to solve this problem. As you can see, federated learning is a distributed machine learning paradigm where devices collaboratively train a shared global model without sharing their raw data, but share the updated model. In this way, it protects the data privacy. Let's give an example of the federated learning in hospital application. Imagine we want to train a model to make predictions for personal healthcare. What's the problem with that? Firstly, the patient's data need strict protection. And also, we need the collaboration of multiple hospitals, since the patient's data in a single hospital can't be enough. In this scenario, federated learning would have a better performance compared to traditional machine learning. You can see in the picture each hospital train model with local data, and finally we can use the learned global model to predict personal healthcare. So how exactly federated learning works? I can introduce it in detail. At first, the federated server shared a model copy to all the participants, and then each participant trained the local model with local privacy data. After training, each client sends the updated model back to the server, and finally, the server can aggregate the contributions from all the participants, and we can get a well-trained model. This is how it works. And I should mention the challenges of federated learning. As we can imagine, since it's a distributed system, it needs frequent communication between server and client, and the communication bandwidth is expensive, so we need to consider the limited resources. The second challenge is the large number of workers. Imagine there are thousands of workers. We can't send the model to all of them and train the model. So how to pick a subset of workers to participate in a training task is a challenge. The third challenge is the different worker capability. As you can imagine, different worker or machine have different ability to train the model, and the different worker selections may influence the global training accuracy. So the goal of this paper is to solve these challenges. To be clear, we need to guarantee fairness. Each worker must be selected at least for a certain fraction of time in the long run to reduce the discrimination. Second, we need to ensure the efficiency of our models, which means we need to achieve high training accuracy of the global model and maximize the total utility of workers. There is some related work trying to achieve the goals. The first one is called worker selection. To put it simply, it's just selecting the maximum possible number of workers using a greedy algorithm based on each worker's capabilities. But the fairness is not considered much in this algorithm. The second approach is called submodular maximization. It's a mathematical optimization technique. Basically, it's just like modeling the subset selection problem as maximizing the average expecting utility while satisfying the fairness requirement in this scenario. Combined with the related work, then we can formulate the problem. The problem full name is multi-round monotone submodular maximization with cardinality and fairness constraint, aka SMCF. I never seen a problem longer than this one. To be clear, The problem is to find a subset that can maximize the submodular utility function in each round with fairness constraint. Obviously, it's an NP-hard problem, which means it can be solved in polynomial time. So we need optimization algorithms to solve it in less time complexity.
No. To apply the approximation method, which had lower time complexity on the MMSM safe problem, we should first clarify several assumptions that help us to simplify the overall problems. Because this is NP hard problem, at first we can assume that it satisfies with the non-term fairness requirement. And in this way, we are enabled to reformulate this problem as a linear programming problem. For the long-term fairness guarantees, it ensures that the fairness over many rounds is satisfied. And it is essential for us to maintain the fairness and encourage sustained participation among workers over multiple rounds. For the linear programming-based reformulation, we assume that the utility function does not change over rounds. In this way, the order of the selected worker sets, such as S1 and S2, does not actually matter, because they will not impact the average utility result. So we can arbitrarily exchange the order of the worker status in the overall problems. We can also simply find an optimal alignment of time fractions among all sets using the linear programming. In this way, we can resolve this problem just by do some linear programming computations. And the objective of our reformulation is to schedule a sequence of S, that is worker sets, to maximize the overall average expected utility F, while satisfying the fairness requirement R. And to be specifically, we adopt the stationary randomized algorithms, and where the workers are selected in each round on a predefined probability distributions. And here we introduce the randomization into our linear programming algorithms. And below, I take an example for this specific algorithm. For example, we have a total of 3 workers inside this FL system. That is n equals 3. And the probability of selecting each worker 1, 2, 3 is Q1, Q2, Q3. And the utility function of selecting each worker respectively is F1, F2, F3. And meanwhile, we also have the fairness requirement R, which equals to 0.2. That means that each worker must be selected at least 20% of the rounds. And our overall objective is to maximize the average expected utility, which is Q1 multiplied by F1 and Q2 multiplied by F2 and Q3 multiplied by F3. And while we have to subject it to the fairness condition, which is that the minimum over the Q1, Q2, Q3 must be larger or equals to 0.2, and the Q1, Q2, Q3 sum equals to 1. So from the above analysis, we can easily see that this is actually a linear programming problem. To solve that, we can actually get Q1 equals to 0.3, Q2 equals 0.5, and Q3 equals 0.2. Meanwhile, we also have the F1 equals 5, F2 equals 3, and F3 equals 4. Then we have already find the schedule that we can produce the maximal utility by doing the weighted average sum of it, and at last we can get a 3.8 as our final output. But for the above analysis, we can see that the algorithm still encounter some time complexity issues. To compute each f, which is the utility of the worker set, we need n to the power of k Oracle queries, and the LP also has an exponential number of variables. So meanwhile, the MMSMCF problem is also a bit hard. So this problem we can use some approximation method to resolve it with less time complexity. Here are two of such algorithms of the fair continuous greedy algorithms called fair CG1 and fair CG2. And we will introduce it respectively in the following. First is about the fair CG1. In the fair CG1, our main goal is to solve the MMSMCF problem by finding a distribution for fractional vector y. In our federated learning scenario, we let the y equals to the probability of selecting each element as the worker. That is the expected time fraction we mentioned previously. And our continuous greedy algorithm is to solve this problem less than the polynomial time solvable in N. And we maintain a vector y, which can evolve during the time interval t. And we start with the vector y equals to 0, and we update in each stage on the coordinates with the maximal improvement. At last, we will get the y1, which can achieve an approximation ratio of 1 minus 1 divided by e. In our algorithm, we have to satisfy two constraints. The first constraint is called the fairness constraint, y, which is the expected time fraction vector, should be larger or equals to r, while less or equals to 1. And the cardinality constraint means that the yt should be less than k. Concretely speaking, the fair CG1 algorithm mainly consists of two steps. In the first step, fair CG1 algorithm employs the fair continuous greedy algorithms in the feasible region PF. And in this way, we can get the fractional vector V1. Each time point, it will find a vector x that maximizes the dot product of x and w, and updates y with the rate of x. In the second step, it mainly performs the randomized dependent rounding function called deep rounding on the y1 we got from step 1 and get the result of workers we selected as ST, which is also the set of K. And next, we will introduce the fair stage 2 algorithm, which is a variant of the fair stage 1. And you can see that only the step 1 of fair stage 2 is different from fair stage 1. It has, but the main difference is that the fair stage 2 has a fine-grained lower bound on the time average utility, which means it can achieve a higher utility than fair stage 1. In the first step, we will start the y0 by r rather than the y0 equals 0 in fair stage 1. And in the intermediate process, yt will always be kept in the feasible region PF. And the same as fair stage 1, we will end with y1. And step 2 is actually exactly the same with fair stage 1. We also choose the randomized dependent rounding algorithms. Here is a summary of the performance over fair stage 1 and fair stage 2. For the fairness, both of the algorithms satisfy it well, and they also fulfills the same equations actually. However, for the lower bound utility, despite that fair stage 1 and fair stage 2 or ensure some lower bound over the utility it can achieve. But fair stage 1 had a more relaxed lower bound, while fair stage 2 had a tighter lower bound. To write that in equation or in formula, fair stage 1 and fair stage 2 or satisfy the following fairness requirement, where the maximal deviation of each element in selection fraction is bounded by some fairness requirement on its upper bound. And for the utility lower bound, fair stage 1's lower bound, although it has, but it's non-trivial, while fair stage 2 lower bound utility is much higher. And according to that, we can see that the fairness requirement becomes more stringent than fair stage 1. So fair stage 2 actually improves on the basis of fair stage 1. Here is a more clear graph that illustrates the overall process of stage 1 and of phase 2. In Federated one, we start from 0, and some points might be not feasible during update process. However, in the Federated 2, our Y0 will start from R, and we finally will get the ideal worker set ST of size K. Concretely speaking, although the updating process varies among the 32 and 31, but both of them, the output Y1 are dropped in the feasible region, and you can see from the graph. Actually, 32 actually represents a quick start process, which starts from R, rather than the 31 has to start from 0 and updates in each round. So 32 can achieves a better performance. For the complexity, in step 1, when we do the discretization process, we actually need 2n to the power of 8 Oracle queries, and in step 2, we actually have to run t rounds. And each round, deep rounding takes at most n iterations. So the running time of the both algorithm will become O(n) to the power of 8 and O(n)t. So we can see that the complexity is still too high. So we have to develop some lower complexity approximations. Maybe we can focus on short-term fairness.
All right. So now let's look at the third algorithm, which is the fair DG algorithm. So unlike the previous two algorithms, which were continuous greedy algorithms and which focused on long-term fairness, this is a discrete greedy algorithm which tries to focus on short-term fairness, and it does it by prioritizing the unsatisfied workers in each round. And as you will see, it also has a much lower computational complexity compared to fair CG1 and fair CG2, since it is a simple greedy procedure. So the simplified version of this algorithm is as follows. So at each round T, it identifies a set UT of the unsatisfied workers whose selection fraction is below the requirement RU. And if the length of such set is less than K, which is the maximum number of workers we can select in each round, then we simply select all the workers. But in the other case, if the length of such set is greater than K, then it greedily selects the K most unsatisfied workers based on something known as depth, which we'll look in a bit more detail later. And the third case is when we do not find any such unsatisfied worker, we just randomly select any K workers to maximize the utility. So now let's look at a example to understand this algorithm better. Let's say like we have 5 workers, N1, N2, N3, N4, and N5. And the maximum number of workers we can select per round is 3. And we need to select at least 40% of the workers in each round. So our fairness requirement R is 0.4. The main idea of this algorithm is, as we discussed, is to identify the set of unsatisfied workers whose selection fraction is below 0.4. So for the first case, let's say like uh, servers, workers N1, N3, N5 were selected twice, and 2 and 4 were selected once. So then at t equal to 6, the selection fractions of N1, N3, and N5 will be 0.4, as they all are selected twice, and there are total 5 rounds. So selection fraction is basically 2 divided by 5, which is 0.4. Similarly, we find selection fraction for N2 and N4, which is 0.2. Since N2 and N4 have 0.2 value, which is less than our fairness requirement, which is 0.4, we add them to the set, and this length of this set is less than 3. So we finally add them to our final result, and we randomly or greedily pick any worker, let's say N1, as our final worker. So the final set in this case will be 1, 2, and 4 for round t equal to 6. Now let's look at another case where the length of our set will be greater than k. So let's say after 10 rounds, N1 and N3 were selected twice, 2 was selected 3 times, 4 was selected 5 times, and 5 was selected 4 times. In this case, the selection fractions are 0.2, 0.3, 0.2, 0.4, and 0.4, 5 and 0.4. So the key thing is here is that we see that there are 4 workers which satisfy the condition, like the N1, N2, N3, and N5 all have selection fraction value which is less than or equal to 0.4. But we are only allowed to select maximum 3 workers. So how do we select in such a case? We can do that by finding their debts. So a debt is nothing but the difference between the selection, the fairness requirement minus the number of times the worker was selected in the previous round. So let's say for N1, it will be calculated like 0.4 minus 2. 0.4 was our fairness requirement, and 2 was the number of times it was selected in the previous round. So its value is minus 1.6. Similarly, we will calculate this for all the other workers. And finally, we will sort them in the decreasing order. And then we will select the top K workers. In this case, it is 3. So we will select the top 3 workers. And here it was N1, N3, and N2. So N1 has minus 1.6, minus 1.6, and N2 had minus 2.6. So hence these were the top 3 workers. And finally, the last case is where we do not find any such unsatisfied worker. And let's say like in this case, we have 5 workers, and the selection fractions all have value greater than 0.4. Then we just randomly select any 3 values, any 3 workers, and it could be anything like N1, N3, and N5. So this was all regarding all the 3 algorithms. But now let's move on to analyzing their performance. So the authors conducted some simulations and evaluated these 3 algorithms on some specific metrics, which were these 4. The first one was performance evaluation, which basically tested how these 3 algorithms performed over time average utility. Time average utility is nothing but the uh, average utility of performance achieved over multiple rounds of worker selection. The next criteria was fairness assessment, which judged whether our algorithms were actually successful in achieving the fairness requirement or not. The third requirement was the analysis of worker selection. So in this case, they looked at a particular worker, and over different rounds, they analyzed its performance. And the last one was just testing the theoretical bounds or the complexity of the algorithms that they proposed. So the first part is the performance evaluation. And the thing common between all the graphs that we will see here is that they have considered one optimal value, which is represented by the red dashed line. And they have and our algorithms are color coded as green, purple, and blue. And for comparison's sake, they have also simulated using a normal discrete greedy algorithm, which is shown by the black dotted line. So as we see here in the graph, all the our 3 proposed algorithms were pretty close to each other, but but fair CG1 and fair CG2 performed slightly better than fair DG. And the thing which is very obvious from here is that DG showed the highest time average utility, which is the topmost line. But it also had a drawback that it did not satisfy the fairness requirement. So this graph basically shows the workers that were selected. And as you can see, the black lines show the workers selected over multiple rounds for DG algorithm. So we see that DG algorithm only selected the same set of workers every time. So this was the thing that they wanted to tackle in this paper. And as you can see, all 3 algorithms actually were successful in achieving this requirement. And all 3 algorithms had their values pretty close to the optimal value, which was red one. And all 3 other algorithms are denoted by all these 3 colors. So in this case, our criteria again was successful. The third one was analyzing a particular worker over different rounds. And this is in here we see authors analyze that the fair DG algorithm converge much faster than the continuous greedy algorithms. And the last one was nothing but analyzing the time complexity by varying the requirement ratio. So the beta actually represents the fairness requirement, and they simulated the algorithms by increasing the fairness requirement and tested whether it is actually close to 1 minus 1 by E or not. But in fact, it actually all three algorithms on even if we increased the fairness requirement, all the algorithms had very good approximation ratio, which was close to 1. So in conclusion, the paper proposed 3 different algorithms, FAIR CG1, FAIR CG2, and FAIR DG, to solve a particular problem in federated learning. And the key novelty here was that they developed approximation algorithms which maximize the submodular utility, while also respecting the cardinality and long-term fairness constraints. And a couple of things which could be researched in future based on this would be like in this paper they did not really provided much guarantee over approximation for a theoretical guarantee for fair DG algorithm. So this could be something which could be explored further. And also here they just considered just one type of utility function, which was I guess training accuracy. But since machine learning, there are many types of machine learning tasks, and every machine learning task might have different type of utility or some criteria. So maybe that could be incorporated in future, and that is something that whether these algorithms are able to handle different type of utility functions or not. So that could also be something which could be explored further. So yeah, that was it from our side.